Okay folks, so I think this will probably be the last in the series, if I've got this right, where I'm going to handle symmetries and finally provide the link to all the final Frieze patterns. So, this was a little introduction, it was a summary of my method of encoding this, generating into this. And we're going to handle symmetries. So there is a choice, essentially, or a decision to be made rather than a choice, because I think there's some wrong answers, about when to remove duplicate and remove symmetries. Now it turns out that for completeness sake, for getting all of the children, all the offspring that you need, you don't want to eliminate symmetries too early. So if I have my two quadrilaterals, if I notice they're the same and delete them, I won't get all the pentagons, and if that means I won't get all the hexagons. So at this stage I need to keep them in the system for generation purposes. So that's not the right time to handle symmetry, which means your file, your storage grows because you've got all the Catalan numbers going on. What I would like to point out then is how we get the triangles out of these. It won't be massively mind-blowing, but number one is attached to two places and only one triangle. Number two has 1, 2, 3, 4 triangles. One triangle, 2, 3, 2, 1, 4 triangles. And you will notice, not very trickily, that each of these number of triangles is one fewer than the number of elements in the list. So that's easy to generate once you've got them. Another way this encoding ended up working well for me, this choice of method. So, however, because the symmetry are limited, this coding, which matches our original Frieze pattern from the first video, will appear in other systems. So this coding is for a different octagon, but you might notice it's pretty similar to that one. So how could I check if it matches? Well, if I go back to my original pattern, if I take an existing situation and mark up 2 repetitions, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, which is what I've got here. If this is a repetition, there'll be some point where I slide it along where it will match exactly, where there'll be the same list, and it looks like there. So because this list matches this section of that repeated list, these are translations, and I don't need to draw them twice, because the Frieze pattern repeats, I don't need the repetitions. So that's rotational symmetries of polygons. With reflection symmetries, all you need to do is reverse the order of this list, which is what I did here before realising that the polygon I originally had symmetry, so they would work either way. But there we go, a reversed list matches and therefore is the same again. So that eliminates them, which now means I have up to, I think, tetradecagons. I'm not quite sure how long I left my code running, it might be a bit more, got in a file, in a folder that's linked below, and perhaps in a slideshow following if my editing gets good enough, all of the different and distinct Frieze patterns that are possible with this rule and with this pattern, up to as far as my code went. So the other thing to cap off is how many of these things are there. And given that this is what I was looking for in the first place, and given how hard it proved to find, I was amazed to find once I got these and put the counts in, that this was known. So, as already discussed, there is one triangle. As far as I'm concerned for my final output, there's actually only one quadrilateral, and as far as I'm concerned for my final output, there's only actually one distinct pentagon. They're the same, they're just rotations. So there are 3 distinct hexagons, 4 distinct heptagons, 12 distinct octagons, and 27 distinct nonagons, and so on and so forth. Having done this work to find them, I put that number, that list of numbers, that sequence, the OEIS, and it turns out the OEIS reference for 207, which means it's quite an early one. The top description of this is the exact problem I was searching, so I'm a little bit annoyed at my Google that didn't come this up earlier. Something about my skills there. But sequence 207 is this list, and the first descriptor says the number of non-equivalent or inequivalent ways of triangulating polygons. Boom. So it's well known, the quantities. But again, as I say, barring the link I'm sharing below, I don't believe there exists just a list, a database of them. So I ran my values through some more code on Python using the matplot library to color-code these things. They may or may not be interesting in the end. For me, the learning was pretty useful and fun to do. Hopefully, you found it worthwhile. Cheers, folks.